Hello everyone. I'm going to go a little more into conditional probability and just wrap things up on this little topic because this is going to help me with a very extremely useful topic on the binomial distribution, which I think you'll find very helpful. So I'm going to do another example that deal with probability of events. So let's just imagine you have a box that contains 6 red tags numbered 1 through 6 and 4 blue tags that are numbered 1 through 4. And you're going to pick one tag at random from the bag. And we want to calculate some probabilities. One of the things that will always help you find the denominator here, everywhere, almost everywhere, is to figure out your sample space, basically all the possible outcomes. So basically we have 6 red and I number them R subscript 1, R2, all the way to R6. And I color coded them for you just for more clarity. And then I have 4 blue tags. So I number them B subscript 1, B subscript 2, all the way to B subscript 4. So we have 10 possible outcomes. This is called the sample space, sometimes labeled or denoted by the letter capital S, okay? So this is my sample space. And I'm just going to do a few quick questions, but I want to point out some things that I haven't addressed. So what's the probability of getting a red? Well, there are 6 possible options out of 10. So this is where this comes in. The denominator is 10. That's your sample space, okay? So that is 6 out of 10, which is 60%. So if you pick one tag at random without looking at the bag, you have 6 out of 10 chances of picking a red. What's the probability of picking an even number? Remember, these 6 red tags are labeled 1 through 6, and these 4 blue tags are labeled 1 through 4. So the subscript gives you whether it is even or odd. Makes sense? So what's the chance of picking an even tag, whether it is blue or red? We don't care. So when you don't see here red or blue, it means we don't care, right? We just care about the word even. So there is this guy, 2, 3, 4, 5. So there are 5 out of 10 options again, which is 50% chance. What's the probability of picking red? And this is called a conjunction. And sometimes we give it a symbol called intersection. So you could say probability of red intersecting even. It's called a conjunction. Conjunction. Okay? I chose to use letters so I don't confuse anyone. Okay? So what's the chance of picking red and even? So it has to be red and even. Now whether you say red and even or you say even and red, it doesn't matter, right? Intersection is commutative. A and B or B and A mean the same thing. So we're going to pick red, and at the same time it has to be even. So we have 1, 2, 3. So there are 3 out of 10 chances. Okay, so that's 30%. So next one is or, not and, but or. Or is called the disjunction. And usually we give it a letter, give me 1 second. A letter, the symbol U, union, or disjunction, not conjunction, but disjunction, okay? So let me erase so I don't confuse anyone, okay? And let me erase this as well. Give me 1 second. Okay, so what's the chance of picking red or even? This or is the mathematical or as explained before, which means either red or even or both. That's what it means. So if you remember the formula for or, P of A or B is P of A plus P of B minus P of A and B. So basically you do this plus this minus that. Makes sense? So 60% plus 50% is 110%, minus 30% is 80%. Okay? So there is an 80% chance of picking either red or even or both. That's the mathematical or, okay? And of course, I can do all of this using a Venn diagram. I have two variables. One is the color called red, and the other one is the parity, even, odd, right? So there is the even and there is the red. Just like what we did with math and science, we can use a Venn diagram and answer all of these questions if we care. So what's the probability of picking neither a red nor an even? So we don't want it to be red and we don't want it to be even. That means we want it to be blue and odd. And that is this guy and this guy. So there are 2 out of 10 again. See how the sample space is helpful? So that's 20%. Now, what's the probability of picking red given, I forgot to mention, the symbol for given, I have been writing given before, is this symbol here, slash, like that. Okay, so that's just given. That's just a conditional probability. What's the probability of picking red given that it is already even? Okay, so of course you can use the formula. P of red given even is P of red and even divided by probability of even. You could use the formula. Or we can visualize this. Remember, you start with the condition. Out of the even ones, we don't care about the odd ones, out of the even ones, how many of them are red? That's what it means. Out of the even ones, and there are only 6 even, I made a mistake here. Red, even, how many even? 1, 2, 3, 4, 5. I made a mistake. No, I didn't. Out of the even, how many of them are red? Well, this even is red, this even is red, this even is red, this even is not red, and this even is not red. So there are 3 of them, these 3. Okay, so it's 3 out of 5, which is 60%. Okay, if we have a little time, I'll do a Venn diagram and we can answer some of these questions really fast. What about, remember, the conditional probability is not commutative. P of A given B is not the same as P of B given A. Don't forget that. So now, what's the probability of having even given that it is already red? So out of the red, considering only the red, how many of them are even? Well, let's look at the red, this number. Out of the red, we have 6 red, so I put 6 here. Again, on the conditional probability, it's the time you don't write 10 anymore, okay? So out of the red, in which we have 6, how many of them are even? There is this one, and that one. Okay, so it's 3 out of 6, which is 50%. Once again, you can use the formula of P of even given red is P of even and red divided by P of red. P of even and red is this one, that's 30%. Let me see if it's true. So we got 30%, which is this one, divided by the probability of red, which is 60%. So 30% divided by 60% is 50%. Right? So that's what it is. 30% is 0.3, 60% is 0.6, 0.3 over 0.6 is 3 over 6, which is 1/2, which is 50%. Okay? So if you want to use the formula, feel free. Okay? But you don't have to. So now I put a little notation for you. What's the probability of picking X? What does X mean? It means one random tag, right? It doesn't matter what color it is. The probability of picking a tag whose digit is less than 4, whose value is less than 4, given that it is odd. So out of the odd ones, how many of them are less than 4? See how I do it? Out of the odd ones, how many of them are less than 4? Out of the even, how many of them are red? Out of the red, how many of them are even? This is how you handle the conditional probability. So out of the odd ones, how many odds do we have? 1, 2, 3, 4, 5. Out of, I made a mistake here, right? I got 5. Let me count again. How many odd? 1, 2, 3, 4, 5. I was correct. No, I'm not correct. So that's 5. Out of the odd ones, how many of them are? I'm going to circle the odd ones so we don't get confused. We have this guy, we have this one, we have this one, we have this one, and we have this one. Okay? So out of these circled ones, called 5 of them, right? Out of the odd ones, how many of them have a digit less than 4? There's this one, that one, and that one. So that's 4/5. See, I made a mistake. 4/5, which is 80%. Okay? So don't get scared of stuff like this. It just means what's the chance or the probability that you pick a number, those indices, those indices or subscripts, less than 4, so either 1 or 2 or 3, given that it is already odd, which means any even numbers, they're not here anymore. So they went camping. These people went camping. We don't talk to them at all. We're only considering the circled ones. Out of the odd ones, how many of them have a number less than 4? And there is this one, and that one, and that one. So this is an exception. So it's 4 out of 5, which is 80%. Okay? Good. Now, I want to remind you that the probability of A given B is not the same thing as the probability of B given A. You've seen this many times, and in here you see that they're not the same. So that's what I'm trying to, but there is a relationship. So what I'm trying to say is this is not this, right? When we say in mathematics that something is not equal to something else, it doesn't mean it is always unequal. It just means it is not reliable. So if I say to you, let's do a little logic for a minute. If I say A equals B, it means A equals B at all times. If I say A is not B, it does not mean that A is not B at all times. It just means A is not always B. In other words, okay, let me maybe this is a bad example. If I say a statement is true, it means it is true all the time. If I say a statement is false, it does not mean it is always false. It just means it is not always true. So sometimes it is true, sometimes it's not true. So we don't rely on it. We say we cannot depend on you. So we call it a false statement. Okay? So for example, if I say, if x equals 2, then x squared equals 4. That is clearly a true statement. This is always true. No matter what x is, if x is 2, then x squared equals 4. Nobody can deny this. But if I write for you this statement, so statement 1, always true. Statement 2, if x squared equals 4, then x equals 2. This is false. Why? Because x can also be negative 2. So if x squared equals 4, it does not mean that x equals 2 all the time. Sometimes, yes, it's true, but it's not always true. Because the answer is x can also be negative 2. Think about it. Imagine x equals negative 2. If I square negative 2, I get 4. Does that mean that x must be 2? I just told you x could be negative 2 sometimes, right? So if x squared equals 4, then x is either 2 or negative 2. That would be a true statement. But if somebody just says this to you, okay, that's a false statement. False doesn't mean always false. It just means it is unreliable. It's not always true. It is not always true, okay? So let's go back here. We say P of A given B is not always P of B given A. In other words, if somebody says to you, P of A given B equals P of B given A, true or false? You're going to say false. It's not true. What it means is it's not always true. So when could it be true? That's the question. When could it be true? So I'm going to show you a trick. So by definition, probability of A given B is P of A and B divided by P of B. And the probability of B given A is P of B and A divided by P of A. That's the definition of conditional probability. Now what I'm going to do is, I'm going to use algebra 1. So I'm going to put a 1 here. I'm going to cross multiply. That means 1 times P of A and B, which is P of A and B, is this times that. This times 1, which is just that, is this times this. Would you agree? So I put P of B times P of A given B. Let's look here. If I put a 1 here, and I cross multiply, I get P of B and A times 1, which is still P of B and A. And remember, B and A is the same thing as A and B. Okay? So these are the same. I can call also this. I can also call it this, right? So this times 1 is this. And this times this is here. Now notice that is that. Therefore, this must be this. Since these two are the same, these two here must be the same. I wrote it in blue. This times this has to be this times that. Now I wrote the word given so I don't confuse you. So what does that mean? Earlier, I said the probability of A given B is not equal to the probability of B given A. However, they will be equal if you multiply this by this weight and if you multiply that by that weight. So if you don't look at these, this equal this is false. However, if you multiply this conditional probability by P of B, remember B comes from here, not from here, and you multiply this conditional probability by P of A, then they are equal. And this is extremely useful in medicine. Doctors use this all the time. If your parents or somebody in your family is a doctor, give them this relationship and tell them and ask them if they tell you if they have used this before. So I'm going to go back here and I'm going to see if it is true. So probability of red given even, we know it's not equal to the probability of even given red. But if I multiply this by the probability of even, remember this letter comes from here, not from here. If I multiply this conditional by the probability of even, and if I multiply this conditional by the probability of red, will they be equal? They better be equal. I just proved it. Well, let's see. P of even and P of red given even is this. P of even is this. And P of red given even is this. So it's 50% times 60%. Here it is. Probability of red and the probability of even given red. Let me look at it. Red, it's this one. And even given red is this one. So multiply 60% by 50%. Aren't they equal? 50 times 60 is the same thing as 60 times 50. And by the way, 50% times 60% is 30%. If you multiply this, 50% is just half of this, right? Half of 60% is 30%. And half of 60% is 30%. So I just verified for you that it has to work, right? Because we just proved that this is true. So this stuff in blue is something you really want to hold on to. And anytime we prove something, I put it in a box for you, or I color code it for you, so it's in a different color, right? So now, for fun, imagine I ask you these silly questions. What's the probability of the entire sample space, like this one? Right? What's the probability that you pick a tag at random and it turns out to be one of them? Well, it's 100%, right? The probability of a sample space is always 1. That's a fact. Now, I would like you to stop the video and think about the probability of the empty sets. It's like a set, like this guy, like this set, but it's empty. This is the empty set. There is nothing in it, basically. It's like an empty fridge or a computer without software. Nothing. It's completely empty. What's the probability of the empty set? So stop the video and think about it and come back. So what do you think? I'm going to use the idea of the complements. Remember, the complement of even is not even. The complement of blue is not blue. The complement of yes, don't say no, okay? It is not yes. And the probability of each is 1 minus the probability of the other. So the complement of the sample space is the empty set. That's the leftover, right? The complement of S is the empty set. And the complement of the empty set is S. Well, if I already know the probability of S, why don't we take advantage of that and get the probability of the empty set? So how do you do it? The probability of the sample space is 1 minus the probability of the empty set. Conversely, you could do it the other way. The probability of the empty set is 1 minus the probability of the sample space. Right? You can also just subtract 1 and multiply everything by negative when you get this. So since the probability of the sample space is 1, 1 minus 1 is 0. So the probability of the empty set is 0. This is a fact, and this is a fact. You don't even have to think about it, okay? All right, now, let me erase this. So I'm giving you a hint here, of course. What's the complement of the entire sample space, okay? So my next question, and I'll end here. What happens if two events are independent? What happens to the conditional probability? Something really fascinating happens. Now, first of all, we need to understand the word independent. So this is a new concept. A and B are independent concepts. It means independent events. It means that one happening has no bearing on the other. So I'm going to give you two events, and I want you to think with me about whether or not those two events are independent. Event A, you studied for your test. Event B, you got 90%. Do you think those two events are independent or dependent? Of course, they are dependent. How about these two? Event A, it is raining. Event B, somebody in Jamaica had eggs for breakfast. Those two events are completely independent. One, eating eggs, has nothing to do with, it is raining somewhere in the world. How about this one? I take penalty kicks, and I happen to play soccer. So I take penalty kicks. Event A, taking the 6th shots. Event B, taking the 7th shots. Now we know you'll either score or not score. Do you think those two events are dependent or independent? I can almost guarantee you that they are dependent. Either that the 8th shots or the 80th shots you're getting tired, right? Or maybe you missed the 7th and it had an effect on you, so you didn't shoot well on the 8th. Maybe you got a little practice by the time you get to the 7th, so the 8th one, you had a better strategy on how to shoot the ball, right? So those two events are dependent. So how do we calculate those? How do we figure out if events are independent or dependent mathematically? Here is how it works. There are many ways to do it, but I'm going to show you a very shortcut, okay? So let's pretend I'm looking for the probability of A given B, okay? Well, the probability of A given B, as you know, is P of A and B divided by P of B. Isn't that true? But if the event A and B are independent, the probability of A given B, A does not depend on B. If they are independent, if A and B are independent, then A could care less what B does. And therefore, probability of A given B is just the probability of A. It's like A saying to itself, what's the chance that I happen assuming B happens? But I don't care about B. So the chance that I happen under the condition that B happens is the same thing as the probability that I just happen. I could care less about B, right? So if you find out that P of A given B, you do this math, and you get some number, and then you compare it to P of A, you compare this answer to the answer you get for P of A. If these two happen to be equal, then the events are independent. So let's look back here. The probability of even given red. Well, if the idea of even and the idea of red, if those two events are independent, then that should give me this. They happen to be equal. Does that mean that being even and being red are independent? Possibly, because they're equal. But it is possible that it's just a coincidence. So let's look at the other one. I want to compare probability of red given even to the probability of just red. Well, they happen to be equal again. So it seems to me that a tag being red or having an even subscript have to be independent, because the probability of red given even is the same thing as the probability of red, because red doesn't care about what even says. So if red and even are independent, then the probability of red given even is just the probability of red, and it is true. And the same thing happens here. So the idea of being red and the idea of being even are independent events. And I can promise you that being blue and being red, even, or being blue and being odd, or being red and being odd, they're going to be independent events. So to make the story short, and I know I went for a long time, if A and B are independent, then P of A given B is the same thing as P of A. Similarly, P of B given A is just P of B. Okay? That is one way to prove independence. There are other ways that deal with the conjunction, P of A and B. But for now, you don't have to worry about it. So to prove that two events are independent, you just have to check either that these two are equal or check that these two are equal. Okay? So now, I'm going to give you an assignment, and then I'll give you a brain teaser, and then I'm going to give you the answer to the previous brain teasers. Okay? The assignment is short. You're going to throw a dice and assume it is fair. In other words, it's not loaded. The chance of having a 1 or a 2 or a 3 or a 4 or a 5 or a 6 are the same. What's the probability that you get a 6? These are really easy. What's the chance of getting a 6? Remember, these are labeled 1, 2, 3, 4, 5, 6. What's the probability of getting a 6? I put 6 in quotation marks just to tell you that it is the face is 6. It's not, it doesn't mean some number, weird number. It's just the actual pretend 6 sits here, and 1 sits here, and 2 sits here, and 3 sits here, and 4 sits in the back there, and I'm missing 1. Oh, the one outside. Let's call it 1, 2, 3, 4, 5. Let's see. Okay. What's the probability of getting either a 5 or a 6? You got to use the formula. What's the probability of getting a number less or equal to 2? In other words, 1 or a 2. Okay. What's the probability of getting a 3 and a 2? So these are really easy. This one, I'm asking you to throw now two. I made a mistake here. It's not dice. You throw in one fair die. I believe the singular to dice is die. D-I-E. Okay. Now imagine I have two. I have two dice. Okay. Sorry. Okay, and you throw them at the same time. And I would like you to find the probability, or you can't just get a number now. You're going to have to get a pair. What's the chance? What's the probability of getting a 3, 3? So a 3 pops up like this. You get a 3 and a 3, let's say. Okay? What's that chance? What's the chance? So imagine this is the variable that deals with this die, and this is the variable that deals with the other die. What's the probability of getting a sum that is 7? For example, you get a 3 and you get a 4. Or you get a 2 and a 5. The sum is 7. And then finally, what's the probability that the sum is less or equal to 5? Okay? So so these are a little harder. They're not hard. They're just a little harder than these ones, okay? So this should take you about 10, 15 minutes max. Okay, so for fun, if you would like, I would like you to work on these two brain teasers. What can you always find in the middle of a taxi cab? The key word here is always, okay? And don't say something like, the glass. Well, that wouldn't be a brain teaser. And how do you know it is in the middle? So that's the first brain teaser. The second brain teaser. Here is an equation. We know this is not true. 62 minus 63 is negative 1. Make this equation true by moving 1 digit. Now, when I ask students this question, they move, let's say, 2 here, and they move 6 back here. Well, that's moving 2 digits. You can only move 1 digit. For example, you could put 6 here. It'll be 2 minus 63 is 16. That's still false. You can only move one of these 5 digits anywhere you want. Don't commute, don't permute, don't flip-flop these, for example. Like, oh, you know what? Let me switch this around. Well, first of all, it's false because 62 minus 36 is not 1. Second of all, you actually moved 2 digits, didn't you? The 3 went here and the 6 went here. You can only move 1 digit and make the equation true. I had a 4th grader once did this. I was really impressed. He said, I'm going to take this dash here. See this equal sign? I'm going to take one of those two. I'm going to remove it. Sorry. And put it here. And now 63 minus 1 is 62. The problem with this is that's not a digit, is it? You cannot move these symbols. You got to move a digit and only one and put it wherever you want. And just a little hint, don't move 1 anywhere, because if you move 1 anywhere, you're going to end up with equal blank, right? So that would be silly. So clearly you're not going to move the 1. You're going to have to move either this 3 or this 6 or this 2 or this 6. Finally, the brain teaser that I gave you last time. How many times can you subtract 5 from 20, I said, right? So some of you said 4 because you start with 20, went down to 0. So you subtract 5 4 times. The problem with that is, what makes you stop at 0? Why can't you keep going, right? -5, -10. So some of you said a better answer would be infinitely many times. So 4 is wrong, okay? 4 is wrong. Infinitely many times is a better answer, but it's still wrong. So the answer is this. How many times can you subtract 5 from 20? The answer is once. Because once you subtract 5 from 20, it's no longer 20. It's actually 15. So the answer is once. And the other question that I asked you, which is a little harder, I gave you this sequence: 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 1, 2, 2, 1, and I asked you for the next term. And a couple of students actually got it. The way you do it, again, I told you, you don't have to do math at all. Just say the number. You have 1. How many of the ones you have? You have 1, 1. So you write it down. I'll repeat. What do you see right now? You see 2 ones, right? There are 2 of them. 2 ones. So you just write 2 ones. Now what do you see? I see 1, 2, and 1, 1. So you write it down. 1, 2, and 1, 1. Now what do we see? We see 1, 1. Don't combine it because you got to go in order. You see 1, 1. Here it is. 1, 2. Here it is. And 2 ones. Here it is. Therefore, what's the next one? I see 3 ones. 3 ones. Then I see how many 2s? I see 2 of them. 2 2s. So just write it down. 2, 2. And then I see how many 1s? I see 1 1. So you just write it down. Okay, if you want to do one more very quickly, I see 1 3, and then 1 1, and then 2 2s. I'll repeat: 1 3, 1 1, 2 2s, and 2 1s. The next one is 1 1, 1 3, 2 1s, 2 2s, 1 2, 1 1. Okay? Have fun with these. These are fun, okay? So let me erase this. You don't need it. So these are the 2 brain teasers. They're also interesting. Try not to cheat and stuff. You know, just keep thinking about them. Whether you get them or not is irrelevant. The idea is to engage your brain. They really help you with your lateral thinking. So just keep thinking about them and think outside of the box and see if you can get them. Sorry, the video is a little long, but the assignment is short. So have fun. Take care.